All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. We're continuing our discussion on the periodic trends, and I just wanted to bring us back to this particular point to show us all the different trends that we're going to look at. And really, today, what we're going to be tackling in this video is looking at atomic radius and ionic radius, as well as cations and anions. So that's where we're going to be moving. And I hope you're ready. It's going to be fun. Let's do this. So we had mentioned earlier, and before we jump into that, I did mention about how we could look at ground state electron configurations and we can make predictions about how the configurations are going to end. And so when you're looking at the first column, they always end in NS1, where N is that principal quantum number. NS2 for the second column, and then so on and so forth, right? Like NS2, ND1, once we get to the fourth row, the transition elements with manganese, NS2, ND5, zinc, and anything in the column with zinc, NS2, ND10, so on and so forth. I think we're understanding the pattern that we're seeing by looking at those ground state electron configurations. All right, so that leads us to our first periodic trend. Let's go. So half the distance between the nuclei of identical atoms that are bonded together is the definition of atomic radius. Now you can look at the image that we have here. We have two chlorine nuclei, and so you've got the distance from this chlorine nucleus to this chlorine nucleus. That's 198 picometers. But then the atomic radius, so the individual radius of one chlorine atom, would be half the distance. So they go from nucleus here to the edge here, and that's roughly 99 picometers. Now, the trend for atomic radius is pretty straightforward. As you go across a period, what we find is that the radii of an element decreases from left to right. Now, as I'm going through this video with you guys, as we're looking at all these trends, we're going to constantly be pulling it back to how does this relate to effective nuclear charge and how does it relate to Coulomb's law. And so as we move across a period for atomic radius, as we move from left to right, effective nuclear charge is increasing, which means that the pull of the nucleus is stronger, which is going to cause that radius to decrease. So that means that the proton has greater attractive forces with those electrons, and it's pulling them closer together, making the radius smaller. Now, as we move down a family, the radii is going to increase. Now, that should make sense because as we move down, we're adding an additional energy level. And so what that means is we're going to be getting a larger atom. And as a result, farther distance, less attractive forces, it's going to get larger. So the highest energy level occupied by electrons increases as you move down an energy level, and so the distance electrons are from the nucleus also increases. So we can see here with this particular trend how effective nuclear charge and Coulomb's law can be used to explain them. Now, if you're looking at the arrows and wondering why are there these random arrows here, so this is showing you how atomic radius increases. It increases as we go from right to left, and it increases as we move down a group, where ultimately, if we move to the bottom left of the periodic table, that's going to be our element that's going to be the largest, which should be francium. Now, the next couple of slides are going to be showing you some data to look at atomic radius as it compares to group number, right? And so as we can see here, as we move down a group, so hydrogen to lithium to sodium to potassium, rubidium to cesium, we see that the atomic radius is getting larger. And there are some exceptions, and I do need to mention that. When we look at periodic trends, they are trends. They don't necessarily mean these are periodic absolutes. There are going to be some things that don't match up nice and neatly with the trend. But everything we look at, we should be able to explain why we're observing what we're observing. And so overall, the trend is as you move down a group, the atomic radius gets larger. All right. This particular graphic, it actually gives you atomic radius values, and you can actually look at the numbers as we move down a group. You got hydrogen at 37, lithium 152, sodium 186, potassium 232, rubidium 248, cesium 265, francium 270. So we see very clearly that as we move down, those atomic radii increase. Now, if we look at it going from the other direction, we can look at, like, if we're in the second row, neon's at 71, fluorine 72, oxygen 73. We got nitrogen, which kind of doesn't fit here with our trend, but 70, then carbon 77, boron 86, beryllium 111, and then lithium 152. So we see that general trend that as we go from right to left, the radius gets larger. All right, which now leads us into ion size. And we're going to talk first about cations. Now, just as a reminder, a refresher, remember a cation is going to be something, a positively charged ion, where its parent atom has lost electrons. So it has a positive charge. So your cations, when we start to look at them, in general, they're going to be smaller than their neutral counterpart. Now think about why that might be. Cations are going to be smaller than their parent atom because the number of protons in the nucleus has stayed the same, but the number of electrons has changed. So we've essentially increased the effective nuclear charge of the nucleus, and so it's able to pull more effectively, and so it makes it smaller. Now, cation sizes generally decrease from left to right as effective nuclear charge increases. This follows the same trend as the atomic radius trend. And then cation sizes increase down a family as valence electrons' distance from the nucleus also increases. Again, that follows the atomic radius trend, and as you'll see with the cation trend, or the anion trend, it's going to be the exact same. It's going to follow that atomic radius idea. Now, your anions, these are your negatively charged ions. These are the ions that have gained electrons in order to satisfy their octet, and so they've gained additional electrons. Now, our anions are going to be larger than our parent atom, and I want you to think about why that's going to be true. Your anions, the neutral counterpart, has same number of protons, but equal numbers of electrons. But when you add additional electrons to the anion, the number of electrons increases. It now outweighs the number of protons, and so now there's going to be increased repulsions in that valence shell, which causes it to be larger. The nucleus can't pull on all the electrons as effectively, and so it gets larger. Hope that makes sense. Now, as you're looking at this slide, it introduces this term. It says for isoelectronic ions, anions. That word isoelectronic means same electron configuration. Okay, so isoelectronic simply means same electron configuration. If we're looking at anions with the same electron configuration, the ionic radii is going to decrease across a row from left to right as the effective increases, again follows the atomic radius trend, and then the ionic radius is going to increase down a family as the valence electron's distance from the nucleus increases. Because the electrons are getting farther away from the nucleus, the distance is now farther, therefore the size is getting larger. Again, it follows the same trend as atomic radius, it follows the same trends as cations. So atomic size, atomic radius, and ionic radius are essentially the exact same trend. Okay. Now, here's some data that's going to show you the differences between those radii. So what we've got on the left, you've got neutral metal atoms, and then you've got their cation counterparts. So notice the drops in the radii of the cations compared to their neutral counterparts. And then when you look at the anions and their neutral counterparts, notice how the radii increase in size as we do that. And I like this piece of data because it just shows you visually what I was communicating to you. So it's one thing for me to say things to you, but to be able to show it to you and to put numbers to it, I think that really helps kind of solidify that particular idea. Again, here is another way that you can look at ionic radii. And you start to see that things don't follow nice and easily as it did before, but we do see these increases in the sizes of our particles. And so in general, what we can deduce from this is that anions are going to be larger than cations. All right, so that brings us to the end of this video, ladies and gentlemen. I just wanted to tackle atomic and ionic radius in this particular video. I hope I've been clear. I hope that made sense. Obviously, if you have any questions, feel free to bring them up in class, and I'll do the best I can to cover them. Thank you guys so much. See you soon.